When we first started learning about fluids, I said that fluids obey all of the same laws that other matter does, F equals ma, etc. So we have looked at forces on fluids, and what we're going to look at next is energy of fluids. So let's imagine that we have some water in a pipe or something, and it's flowing through the pipe. So we can think of, we can think of this as a like continuous flow, or we can think about a like chunk of the water in the pipe. So if we think of some little blob of water that has mass m, and if it's flowing through the pipe, this chunk at some mass has some velocity, and maybe it's at some height above the ground, right? So we can think of this blob of water as having some energy that we can identify, right? It has kinetic energy because it's moving, and it has potential energy because it has this height above the ground. So our total mechanical energy is going to be equal to our kinetic energy plus our potential energy, K plus U. So this is equal to, 1/2 mv squared plus mgy, like we've learned, so many times. It turns out that in general, it's not super useful to think about the mechanical energy of a blob of fluid, and rather instead think about the energy density of the fluid. So no matter how much of it we have, we can think of each little piece of it as having some energy density, right? This energy, whatever energy we got for this blob, is spread out evenly over the blob. So let's instead think about, how much energy we have per volume of stuff in the pipe. So to get that, we just need to divide this by volume. So our energy density is equal to 1/2 mv squared divided by our volume, capital V, which I will write like this, and mgy divided by our volume, capital V. Now we're not going to, this is the volume of whatever blob of mass we're talking about. We're going to divide these, and we're not going to have to worry about what the actual volume is in just a second here. So notice this m over v, mass over volume, that is our fluid density. So this becomes 1/2 rho v squared, where this v is our velocity, plus m over v is rho gy. So 1/2 rho v squared, this is like a kinetic energy, but it's a kinetic energy density. It's kinetic energy per volume. Rho gy is our potential energy density, that is like a potential energy per volume. There's one other term that we need to add to this, and that is our pressure, P. And we're not going to worry about why this is, but we can kind of think about it kind of taking the place of spring energy. So if there's a pressure on our fluid, we are like exerting a force on it to compress it, and it can push back on us and do work. So really the pressure here is kind of like, in addition to kinetic and potential energy, if our system is at some pressure, it has an ability to do work on something else, to exert a force on it, and transfer some of that energy to it as it pushes on it. So our pressure is another form of energy density. Like I said, we're not going to worry about why that is or where it comes from, but that needs to be included here. Okay. So what can we do with this? So this leads us to an important equation called Bernoulli's equation, which states that the energy density is constant along a line of flow in a fluid. So if I have some fluid at point A, and this fluid flows over here to point B, no matter what, maybe this is through some crazy pipe or under some river or something like that. We have fluid flowing from point A to point B. The energy density at point A has to be equal to the energy density at point B, which means this equation at point A has to equal that equation at point B. So this gives us something long to write down, because at points A and B, we might have a different velocity. We might have a velocity at point A, a height at point A, and a pressure at point A. And we have all those same things at B. We have some maybe different velocity, some maybe different height, some maybe different pressure. And so we have the following equation. So this is Bernoulli's equation: kinetic energy density plus potential energy density plus pressure at point A equals all of that same stuff at point B. So this is a big, intimidating looking equation, but remember, it's just kinetic energy, potential energy, and pressure at point A and at point B. All right. So if we're going to use this equation in a problem, we need to identify what point A and point B are. That is a very important step. You have to know where you're talking about. And then you also want to identify which of these variables are the same. This won't always be the case, but I think in all the problems I'm going to give you, at least two of these, or excuse me, at least one of these variables is going to be the same at point A and point B. The fluid is going to have the same velocity at point A and B, or the fluid is going to be at the same height at point A and B or something. When that happens, if YA equals YB, these potential energy terms would just cancel out, and you can, if you recognize that, you can not write them down in the first place, which means instead of 6 terms, you only have 4 terms to write down, and so on. So problems with Bernoulli's equation end up looking like our energy conservation problems from chapter 7. We figure out what kinds of energy we have at the beginning, kinetic energy and pressure and no potential energy, and use that to figure out how much energy we have at the end. The fact that we're talking about energy density instead of energy doesn't really make a practical difference. We're still doing something like solving for the unknown velocity at the end point at point B, or something like that. So being able to identify what's going on at point A and point B, that is the most important step to solving things with Bernoulli's equation. Also look for, in addition to looking for things that are the same, look for things that are 0. That often also helps simplify this equation. If your fluid is at rest at one point, that of course means that your velocity is 0, so there's no kinetic energy, and so on. Sometimes in Bernoulli's equation problems, we run into situations where the velocity isn't 0 at one point, but it's very, very low, or much, much lower than the velocity at the other point. In which case you can still say that you can treat the velocity as 0 and say there's no significant amount of kinetic energy there. I'll point that out in at least one example we do in the near future. One other thing to point out is, so we've had these pressures here, and we've learned about both total pressures and gauge pressures. And should these be total pressures or should these be gauge pressures? The answer is it doesn't matter as long as they are the same. So if you're measuring two gauge pressures, that's okay as long as they're measured relative to the same environment, right? So if you're looking at flow through some pipe from point A to point B, and your pressure at point A is a gauge measurement made, between the inside and outside, you can also have the pressure at B be a gauge measurement as long as it's measured between the inside and outside also. So in other words, these two pressures either have to be both total pressures or both gauge pressures, but either one of those is acceptable.